So we shall start today with an informal introduction of stochastic processes. So this will be the first of a series of classes about stochastic processes, Brownian motion, and what is a stochastic equation and how it can be treated mathematically and manipulated. Especially this will be important for what is called the Ito calculus. So this informal presentation, I will start with the space of we have a probability space defined by event omega, the ensemble F, and the probability measure on this set F. This is called a probability space, and I assume probability space, and I assume that this is well known. And on this we can define what is called a stochastic process X, which basically take its value in omega and R into, let's say, a space such as R or Rn, such as we have an event and the time t, and this is denoted x omega t. Another notation is x omega and t. So such application has some properties such as it is continuous in t and measurable with respect to the set F here. It is measurable in omega, which is the event. So this is the basis of the object that we are going to manipulate and precisely do some calculation with this stochastic process. So this is by definition, X is by definition a stochastic process. And the first, and I think the most important, is called the Brownian motion. There are many ways to introduce Brownian motion, and I will, for the time being, I will introduce it by formal properties. So xt, which is a stochastic process, is called a Brownian motion when it has the following properties. For all delta E, so let's call it 1, for all delta E positive, if we look at the increment, so sometimes I also will omit the indexation in omega, so xt plus delta t minus x of t, this is independent of xt or xt of omega. In addition, all the increments are independent, which means that if we look again at this xt plus delta t minus xt, they are all independent, so and this is true also for all t. Not only they are independent, but the distribution is according to a Gaussian variable. It's a Gaussian, so this is a Gaussian variable of mean 0, and let's say of variance, it can be of variance 1, or a variance, in that case it can be a variance which is 2d delta t, and we know this n0 2d delta t. And for example, the probability density function in dimension 1, the probability to start from position y and to make a transition to x during delta t can be written as 1 divided by 4 pi d delta t. So this is 4 pi d delta t multiplied by the exponential of minus x minus y squared divided by 4d delta t. Note that this expression is symmetric in x and y. So we have here a symmetrical expression in x and y. This can be this formula can be generalized in n dimensions, such as in Rn, where the probability density function p delta t of the transition from a vector x to a vector y, so x is a vector in Rn, is equal to 1 divided by 4 pi d delta t to the power n divided by 2 exponential of minus x minus y squared divided by 4d delta t. And this is the Euclidean norm. This is the Euclidean norm. So this definition is very important, and so in general, let's explain the, what we have discussed here. Suppose we can restrict the definition of the space by imposing, for example, at t equals 0 that all trajectories start from x0. So a realization is a path up to time t, and this is called x omega of t. And we have other paths, so x omega of t is the position here at time t. So we get this point. And of course, the space is a concatenation of all of this space when t goes to infinity. So this is another realization, x omega of t. So this is omega 1, this is omega 2, this is omega 3, x omega 3 of t. And if we want to look at the entire path, we can take, for example, x omega s and look at the ensemble from s going to t of the union here of this x omega s. So there is the tribute and all of this ensemble that can be generated in the classical probability ways that I'm not going to explain here. So there are quantity that are important, and those are called the average over the realization, which is called the expectation. So the expectation is the average over the realization, average over realization. So you have many realizations. We can define what is called the expectation of x omega of t, which means average over omega. And by definition, when, for example, we can condition that the position at time t equals 0 is a point x0, this is exactly given by the integral of x multiplied by the transition probability from x0 to x. And here we need to average over, so this is the same x, so we have to average over dx. So if, for example, in dimension 1, this will be R. If you have a manifold, this should be V, or Riemannian manifold. Or it can be, for example, Rn. So this is a definition of the expectation. So expectation again means we average over the realization, which are connected to this probability density function, which allow us to calculate it when we know this p of t. And this is also an important definition when we want to calculate this using empirical data. So for example, if we have a collection of points and we look at the average of x omega k of t, when assuming that omega k are a good sample of your distribution. For example, suppose we have a countable set such that this becomes, let's say, xk of t, and we need to average over k, so 1 over m from k to n. So this is usually converging as n goes to infinity, so we multiply by 1 over n to this expectation of x. So this is the empirical sums that can be used to approximate and to create estimators of the average. So this is as n goes to infinity, it converges here to this quantity. So for a general function, we have the expectation of phi of x of t that depends on omega, condition that x omega of 0 was equal to x 0. So this is again the integral over the domain, let's say r of phi of x pt of x, condition that at time 0 the process is started at x0 and we have to integrate over the measure over the space. So by definition of the Brownian motion, since the increments are all independent, this says that if we average over the increment, so average over this little omega of xt plus delta t minus x of t, this is exactly 0, which means that this is the exact translation of the fact that it is independent. Now, Brownian motion are characterized by the first two moments, so this is the first one, and then we have to look at the second moment, which is the expectation of x of t plus delta t minus x of t squared. So I will do here the calculation in dimension 1. This is the same in all dimensions, since all projections are all Brownian motions. So in n dimension we have a sum of what we are going to calculate here in dimension 1. So this can be calculated. It is the same really, and we can show that this can be shown as an exercise of x of delta t minus x of 0 squared. And this can be calculated using the general function that we just discussed, assuming that x0 is equal to 0, which can always be done by translation. This is only x squared, the probability transition function from 0 to x during a time delta t dx, and this is can be calculated as twice the integration from 0 to infinity, twice because here we have in principle to integrate from minus infinity to plus infinity, and then x squared exponential minus x squared divided by 4 delta t d divided by square root of 4 pi d delta t dx. So this I will leave the result of the calculation. This has to be integrated by parts. So one integration by parts leads to the following result. We obtain 4 delta t d integration from 0 to infinity of exponential minus u square du, and this is the classical Gaussian integral, square root of pi divided by 2, so we obtain in the end 2 delta t d. And if we have a process in n dimension, xt plus delta t minus xt. So calculating here the Euclidean norms is going to be the sum over all the expectation over all coordinates, so xi of t plus delta t minus xi of t, and this is squared, and using this calculation, since they are all the same, this is n times the result that we have in here. So this is 2n d delta t. So this definition is important because this is the way also to generate what is called random walks, which are approximation of the Brownian motion at a time scale delta t. So this is numerical implementation. How we calculate implementation, how the random walk is simulated. So a random walk. So let's assume that we fix a scale delta t. So this is exactly the following formula: xt plus delta t equals xt, and by definition the difference is equal to a Brownian Gaussian variable with variance 2d delta t. So we can write it this way: plus 2d delta t square root, and then we have to multiply this by xi. But this is a Gaussian variable, which is a Gaussian variable that can be generated using any computer. It's a Gaussian variable of mean 0 and variance 1. So for example, if we want now to define to generate this sequence, we can define xn plus 1 equals xn plus 2d delta t xi n. And so if we start from 0, we get the sum 2d delta t, and we get a sum of the xi k from 0 to n. And so this is how to simulate these random walks at a resolution delta t. So note that in this definition there is no condition about what happens if we have a Brownian process at a boundary. So for example, so this is a remark. The process here can be generated, for example, for xn positive. So this can be generated as a random walk here. So this is x, let's say x0, x1, and we have all these jumps. And if we want the process to stay in the positive axis, and if there is a jump from xn here to xn plus 1, then this jump has to be forbidden, and the position here of this point xn plus 1 has to be replaced here. So there is a unique manner to define it such that we get a reflection process which satisfy such that the probability density function satisfy what is called the reflection condition. So to get this condition, that the probability density function is such that dp dx at x equals 0 equals 0. This leads, and this will be discussed in a separate class, to a unique way to define here the position of a point that will be otherwise in the negative part. That is, suppose xn plus 1 equals xn plus 2d square root delta t xi, and suppose this is it is negative, then the way to define xn plus 1, the reflected part, is to take, so the definition would be to take the absolute value of xn plus 1, that is also minus xn plus 1. And so we will see later on that this is the process to generate reflections. Now let's discuss the probability density function in general. So the probability density function of a process, so probability density function of a process xt of omega. So by definition, the probability that a process is located in a little volume around the position x, which will denote x plus dvx, condition that it started at position y, this can be written as the probability to jump from x to y in time t multiplied by the volume element dv of x. So this by definition is the density probability function. And so again, this is the probability that if we think about a ball located at position x, that at time t the process is located inside this ball. This is xt of omega, when the process started before at position y, so it ended up here at time t. So for example, it is interesting that we can now use this framework to write quantities. For example, what's the probability? So this can be seen as the first exercise. Can we write the probability to make a transition? If you have a process, a transition from a point x, which starts in the negative space, to a point y, which is located in a positive space. How can this be written in terms of the probability density function? So this is the probability that such event occur at a time t. So this can be written, since we can start from any negative x. This can be written as the probability density function to start from x and to sum over all x and to arrive here. So we have to integrate, and we have to, so this is in negative x, so I'm going to erase this. This is for negative x, and we need to arrive in the space of positive x. So this is the probability that such event occur in time t. So this is a probability and it's occur in time t. So this exercise, although looks trivial, it is quite instructive, because in many applications, in for example numerical simulation of stochastic processes, in formulation of modeling of molecular event, it's usually a delicate step to formalize the probability density function that we have in mind in terms of the elementary probability density function that can be usually computed analytically or numerically using simulations. Sometimes it can also be analytical. So this is usually a fundamental step to formalize this, to write this the precise expression. Okay, so I'll stop in here the first part of the class. Then I would like to, so in the second part, which we'll do in the next lecture, we'll discuss what is called Markov processes.